Okay, so here we're in section 6.3, and we're going to be talking about the logistic equation. We've been working up to this. Okay, now up to this point we've been solving differential equations which look like this. And they give us P is equal to our initial value times e to the kt, which is exponential growth or decay, depending upon whether it's going up or it's going down. But if you graph these things, what you find is that they're going to look sort of like this, where this is your P naught, and this is time. So these things just grow unbounded. As a matter of fact, the bigger the time is, the bigger the value. Now, what we know is, by and large, this is not really true as biological populations. It's not a lot of true with a lot of other kind of things either. So what we do is we modify this. So we do a dp dt is going to equal to kp times 1 minus p over L. And L is what's called the carrying capacity for biology. Or in other words, this is the maximum amount that can occur. This avoids getting something dumb like 25 million ferrets in a 140-acre plot. Okay? Okay, and so what we do with this thing then, naturally we need to solve it. And we're going to do this with a separation of variables. So we're going to end up with dp over p times 1 minus p over L is going to equal to k dt. Now this is a little bit different, and I'm not going to make a big deal out of this, but the way you have to deal with this is what's called partial fractions, and we'll deal with that, I hope, a little later on in the semester. But if you want to see this, look at example 9 in your book for how they integrated. And ultimately what it amounts to is you rewrite this as 1 over p plus 1 L minus, p minus L. Which is where the partial fraction comes from. Okay, but let's cut to a short story. What happens when you do this is you end up with p, or whatever your variable is L over 1 plus b. This comes from your constant of integration. And it was changed because for some reason other biologists didn't like C. They liked B better. So, and what happens, of course, is that this is e to the c. So they preferred B. 1 plus b times e to the negative k t. And remember, this is your carrying capacity, or the maximum number of things you think you can have. And this thing right here is the pig kahuna. This is called the logistic equation. And this guy is used in more things and more places than I can think of. Obviously, it's used a lot in biology to model populations. but it's also used in some other places. Economics uses this. They're looking for maximum demand for a product. And if you end up with exponential growth, now obviously at some point or other, your demand's going to level off. You don't have an infinite number of people to begin with. And no matter what you put out, someone's not going to like it. So logistic equation is used for maximum demand. It's also used, of course, for supply also on the other end of it. It's used to model spread of diseases. Okay. Now in this case, your carrying capacity is the maximum demand you think people will have for the product. If you know nothing else, it ought to at least be whatever your population is. You're not going to have more people want it than what you have. But spread of diseases, and again, this doesn't grow. Number one, you've got a finite number of people. Number two, not all, some of the people are going to have resistance to any particular disease, and others just won't be exposed to it. And it's also used for the amount in electricity, for the amount of charge in a capacitor. So if you're building up a charge in a capacitor, it's modeled by the logistic equation. And this is just sort of a quick and dirty glance at what we've got. Okay, so let's take a look at an example of how you're going to use these things. Okay, and this is a nice example. This is out of your book, but you can do this with anything. But we had 25 panthers that are released into a game preserve. By the way, this is your initial population. After 2 years, there are 39 panthers. Now, obviously, I'm not good at biology. Matter of fact, I don't particularly like biology. But I saw a logistic equation from an electrical point of view. There's no difference. It's the same basic equation. You just change what you're labeling these things. So this is why I can do biology problems, and I can do disease spread. I can do any kind of communicable thing that spreads through the population, even though I have no medical training and I have no real much background in biology. That's because I understand the differential equations and I understand how to apply them and change them into each particular idea. Okay, now the carrying capacity is believed to be 200 panthers. And they probably got this from historical information. And carrying capacity, of course, is our L. And we want to derive a logistic equation for this thing. So let's do this. All right, now the logistic equation is P is going to equal to L over 1 plus B times e to the negative k t. Now, when you come in, some of these things, especially electricity, L's called something different, B's called something different, K is called something different. But the equation is the same thing. We just changed the letters that we're putting in there. Okay, so now let's come back in and substitute in what we got. We've got L, it's 200 of these little guys. These are Florida Panthers. So it's 1 plus B times e to the negative kt. So we need to find B and we need to find K. Now B, if you remember, is related to our initial population, but it isn't exactly the initial population because we've got this carrying capacity up here. But we still are going to want to use our P0, and we put it in here. So we have 25 Panthers, and it's going to be 200 over 1 plus B times e to the negative k times 0. That goes to 1. So you end up with 25 equals 200 over 1 plus B. Now I cross multiply. So I'm going to have 25 plus 25B equals 200. Subtract 25, 25B is 175, and then divide by 25, B is 7. Okay, so we got our B now, and we've used that point right there. Now we're going to have to use this point to get our K. All right, so our equation now, as we have it, is P is going to be equal to 200 over 1 plus 7 times e to the negative k, and e to the negative k t. Okay, so now we come back in, and we know that at 2 years we had 39 Panthers. Okay, so 39 is going to equal to 200 over 1 plus 7 e to the negative 2k. I plugged in my 2 for that. All right, same idea here. We cross multiply. And I end up with 39 plus 273 times e to the negative 2k equals 200. I subtract 39, so 273 e to the negative 2k equals 161. Then I divide it by 273, so e to the negative 2k equals 0.5897, and then I natural log these puppies. Negative 2k will be equal to the natural log of 0.5897, or k then will be equal to negative the natural log of 0.5897 divided by 2. My k worked out to be 0.2641. Okay, so now we come back in and we finish up our equation. So now we've got P equals 200 over 1 plus 7 e to the negative 0.2641 t. And there's our population, our equation for our population as a function of time. Okay, now another part of this question then asked, how many after 10 years? And this is the typical question EPA asks. So we need to find P of 10, then is going to equal to 200 over 1 plus 7 e to the negative 0.2641 times 10. or population after 10 years is going to be 133 panthers. Please don't give me a decimal. We're not going to have part of a panther. Okay, the other typical question asked then is, how long to get to 80% of carrying capacity? And the reason people ask this is often a cutoff where hunting is allowed. Now, this number can vary depending upon whether you're dealing with predator or not, size of the creature, a bunch of other stuff. But oftentimes it seems like you see them talk about 80% of carrying capacity. Because once we get to that point, then they feel a lot more comfortable about going out and allowing people to start taking at least some panthers out. Okay, so if you remember, our L was 200, and 80% or 0.8 of L is 160 panthers. So that's our population we're interested in. So 160 will equal to 200 over 1 plus 7 e to the negative 0.2641 t. You need to solve for t. Again, we cross multiply. Like we did when we were solving for k. So I'm going to have 160 plus 1400 e to the negative 0.2641 t equals 200. Subtract 160. Divide by 1400, so e to the negative 0.2641 t equals to whatever 40 over 1400 is. Ln these puppies, negative 0.2641 t. Be the natural log of 4 over 140. Go ahead and cross those out. Or t is going to be ln of 4 over 140 divided by negative 0.2641. And when I plug this in, t is approximately 13 and a half years. The same kind of calculations were done for wolf reintroduction in the Intermountain West, especially in New Mexico and Wyoming. And I believe, if I remember right, I got this 80% because that's what they were looking at, is they wanted to get to 80% of capacity before they started to allow people to go in and hunt these kind of things. So these kind of things were also done for this. The same basic equation, the same calculations are done again for disease spread, any kind of population, not just predator-prey, but you can also deal with bacteria. Obviously, there's going to be only a certain amount they can handle there. Viruses are the same kind of thing. Capacitors, anything which starts to show some initial exponential growth, but then tapers off and approaches an asymptotic value, you use this logistic equation to model it. And these are the kind of things you're going to be doing in your book problems with the logistic equation. And as you can see, this is a rather powerful tool. Like I said, economists do use the same kind of thing to model things with. So if you ever get really tired of Mr. McGill or the other, whoever is teaching you on the other end, for a logistic equation element, see what they do with you. I bet they won't like the differential equation part of it.